Analyzing rational functions. It takes a while to draw a rational function, so it'd be good if we could recognize them without having to draw the entire shape. One thing that's going to help us is being able to identify a point of discontinuity. So a point of discontinuity is a hole in the graph. Creates a point at which the function is not continuous. Let's take an example to understand what we're talking about. When you're given a rational function, I'm going to ask you to start by factoring. This is a quadratic, we can factor that. And then you'll notice that these two terms, x minus 3 on the top, x minus 3 on the bottom, are the same. We can reduce that. That gives us y equals x minus 2. Now you've got to be a little bit careful. These two functions are not the same at the moment. X minus 2 is a straight line, whereas this one is a straight line with a hole in it, because you can't have x equals 3. So we must state that x cannot equal 3. Again, where that comes from, if these two functions are going to be identical, and we have eliminated the x minus 3 on top and bottom, we have to state that x cannot equal 3. We knew x could not equal 3 in the top. It can still not equal 3. So we have to tell ourselves this once we've reduced those, because otherwise we might forget. All right, let's find out some information. To find an x-intercept, you start by letting y equal 0. So what would make x minus 2 equal 0? What happened to the 1? I'm just not bothering writing it. So x-intercept, 2. Y-intercept, let x equal 0. Getting a y-intercept of negative 2. Vertical asymptote. We don't really have a rational function anymore. There's no variable on the bottom. And when there's no variable on the bottom, you don't have any asymptotes. If you weren't aware of that, you could do the question anyway. What would make the denominator 0? Nothing. And the horizontal asymptote, we've said compare the exponent on the top with the highest one on the bottom. When the top is bigger, there is no horizontal asymptote. So whether you realize that this was no longer rational, or whether you did the work, you'll get the same answer. Point of discontinuity comes from here. What is x not allowed to equal? And the answer is 3. But where's the 1 coming from? Let's go back to our function. Y equals x minus 2. If we put 3 in for x, oh, we'd get 1 for y. So we know exactly where the hole is. Rather than just a vague hole in the graph, we can figure out exactly where it is. All right, so very rough sketch. Y-intercept, negative 2. X-intercept 2. What sort of shape is that? Should be a straight line. So this is what we would normally draw. Humor me and pretend that that's a straight line. And now we're going to add something new. At the point 3, 1, right here, we're going to put a hole in the graph. So this is what it looks like. So here is our point of discontinuity at the point 3, 1. How does that help? Let's give ourselves some practice with asymptotes and point of discontinuity, and then we'll talk about how it helps. First step, factor. So we took out a common factor of x and a common factor of 2. I'd like you to take a long look at these two terms. X minus 2, 2 minus x. Definitely not the same. But if you look closely, positive x, negative 2, positive 2, these are opposites of each other. And what happens when you reduce opposites? Can you see that you end up with a negative 1? Another way of thinking about it, you have x minus 2 on the top, 2 minus x on the bottom. If you were to factor a negative out, x minus 2 minus, we factored a negative out, that would become negative 2 plus x. You can then see that you end up with a negative 1. So I tend to skip the factoring of the negative and just remember that when I reduce negatives, opposites I mean, I get a negative 1. So those will reduce and give me a negative 1. So y is negative x over 2. Asymptotes and points of discontinuity. Well, x cannot equal 2. Should probably state that. And then there's our point of discontinuity. Whatever this was is our point of discontinuity. Any asymptotes? Nope, this is no longer rational, so no asymptotes for that one. Let's try the next one. Factor the top. A couple of common factors. Take a long look at these two. They are not the same and nor are they opposites. So there's nothing we can get rid of. Is there anything that would make the denominator equal 0? When x equals 2, so that is an asymptote. If the denominator equals 0, you have a vertical asymptote. If you had a common term in top and bottom, there is a point of discontinuity. So that's the difference between them. Denominator 0, asymptote. Same thing, top and bottom, point of discontinuity. Factor the next one. Common factor on the top, difference of squares. These two terms are exactly identical. So we reduce that and state what x cannot equal. What does that give us? Point of discontinuity at x equals -2. Keep looking. Is there anything that would make the denominator 0? We have a vertical asymptote at x equals 2. One more. Factor the top, common factor of 2 on the top, and can't factor the bottom. So nothing was eliminated, so no points of discontinuity. And is there anything that will make the denominator 0? Not that I can think of. Not in the reals anyway. If you were tempted to say 2 or -2, try it. Put 2 in and see if you get 0. You don't. So no points of discontinuity and no vertical asymptotes. So when you're doing these rational functions, you might have a point of discontinuity or an asymptote or both of them or none of them. How does this help? There's an exercise in your homework pack on top of page 4. And we're going to state x and y intercepts, all asymptotes, any points of discontinuity, and then we're just going to look at a graph and figure out which one matches our function. That should be quicker than having to draw the entire thing. So we're going to do exactly what we did on the previous slide. Factor, state any asymptotes, any points of discontinuity, x and y intercepts. Okay, here we go. X-intercept. If we're letting y equal 0, and it's a fraction, only the top can equal 0. So I'm getting 0 and -2 for my x-intercepts. Y-intercept, if you let all your x's equal 0, you get 0. We knew that, because if the x-intercept is 0, the y-intercept is 0. We did not eliminate anything, so no points of discontinuity. And can the denominator equal 0 in this question? I've got a no for that one. So now let's match the graph. Looks to me like this is a vertical asymptote because the graph is approaching it on both sides. So it's not that one. This also seems to have a vertical asymptote. So it's not that one. Well, that should make this pretty straightforward. Let's double check this. X-intercept at 0, x-intercept at -2. No holes in the graph. Must be this one. So the first one, this must be A. Okay, let's try the next one. Start by factoring. Anything we can eliminate? Make sure we specify what x cannot equal. So x cannot equal 2. That immediately gives us a point of discontinuity. And when x is 2, y is a half. All right, so point of discontinuity. What about an x-intercept? Can you make that equal 0? I hope not. So no x-intercept. A y-intercept, if you let x equal 0, you're immediately in trouble. So no y-intercept. Any vertical asymptote? I believe so. There's a clue. When you have a vertical asymptote of 0, that's usually when you don't have a y-intercept. So those two generally go together. Which graph is this? You should by now recognize the 1 over x graph. So the 1 over x graph, we're probably going to look at this one. And look at that. There's our point of discontinuity right there at 2.5. Vertical asymptote 0. So that one is B. Pretty sure you know which one is C, but we're going to go through the whole thing anyway. Factor the bottom. These will eliminate. That reduces to 1 over x minus 2. What was it that x could not equal? Negative 2. That immediately gives us a point of discontinuity. The negative 1 over 4 comes from plugging negative 2 in. X-intercept, can you make the top equal 0? I hope not. Y-intercept, let all your x's equal 0. I'm getting negative 1/2 for my y-intercept. And vertical asymptote, anything the denominator cannot equal. Answer for that would be 2. Let's double check that our graph is right. Vertical asymptote at 2, check. Point of discontinuity, negative 2, negative 1/4, that looks right. Y-intercept, negative 1/2. And no x-intercept. Good. Okay, your job, 1 to 4, your goal again is to get quick at recognizing these functions. You don't want to graph the whole thing. Have fun.